Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Today, inshallah, we will continue talking about estimation and more specifically about confidence intervals. So in this lecture, we are answering the following questions. First, how do we compute a confidence interval? And what do we mean actually by a confidence interval? Then we'll talk about when or why we shouldn't use the bootstrap method in some cases, and how or whether the bootstrap method is related to hypothesis testing. Recall that we started to talk about the bootstrap method last lecture. It is a technique for simulating repeated random sampling. So we start with an original sample, which is large and random, and since it is large, it will probably resemble the population, and we sample from it at random multiple times. So here is what we saw last time. We have we want to get a sample from the population. So we start with an original sample, and from that sample we resample multiple times to get multiple similar samples, and from that we compute our statistic and our estimation. So all of these look pretty similar, most likely, and this is why the bootstrap method works. So on the left, this is what we wish we could get, which is the population. Of course, we don't have the population, but what we have is a random sample from it and multiple resamples from it using the bootstrap method. And the key to resampling is to draw from the original sample at random with replacement with the same size of the original sample, so as many values as the original sample contained. Let's get back to the demo example that we stopped at last time, which is the salaries of the employees in San Francisco. So we read the data. This is the median of the population that we saw last time. Here is the original sample from the population. Of course, this is just for the purpose of the demo. We assume that we have the population, but in reality we don't. Here is the sample from it, the 300 employees sample. This is the estimate from the sample. And then the bootstrap method means that we take this original sample and we resample from it multiple times. We do that here 1000 times. This is the function that will give us from the original sample a new sample with replacement with the same size, and it computes the median salary, which is the parameter that we want to compute. We want to estimate. We'll do that 1000 times, and then we display the histogram. Okay, and that's what we did last time. So from the sample that we got today, here is the distribution of the bootstrap medians. It goes from maybe 90,000 K to about 100 and maybe 7 or 8,000. And last time we computed the middle 95% interval, which is the interval that includes the middle 95% estimates from the samples that we got from the original sample. Okay, so 95% of the values of the 1000 values that we got from the simulation here are in this interval, in this gold interval. Now we see that this interval happened to be to not capture actually the true value of the parameter. Okay, so it happened to be to not include it. Okay, last time we saw from the sample that it included, it captured, it covered the actual value of the parameter, but because we know it in that demo. But in this time, when we got another sample, it didn't, which is really interesting. Now the question is, will that happen again if we do if we repeat that process exactly again? Will that happen again or not? Okay, so let's try it. Let's do what we just did one more time. So now the whole process is that we will take a new sample, a new random sample from the population, okay, and then we'll do the bootstrap method. We'll take many bootstrap samples, and we compute the 95% interval. Okay, let's do that again. So that's a completely new original sample, and we do the bootstrap method over that sample. So let's do that and see what will happen this time. This time, the interval that we got included the known parameter, the true value of the parameter. Okay, so let's do it one more time and see. It included it again. Again, it's included. Okay, you look at the red point, of course. The yellow point is the estimate from the original sample, and it is will always be around the center of the distribution. But we are interested to see how many times or how often the 95% interval that we compute from the estimates using the bootstrap method will include or will cover or will capture the true value of the parameter. It didn't happen, by the way, in the first one. Okay, it didn't happen in the first one, but it happened in the 2 or 3 samples that we got now. So the question is, we can generalize it and ask a general question. What if we did that 100 times? How many of these times the interval, the 95% interval, will capture the true value of the parameter? In fact, the statistical theory behind the bootstrap method says that a 95% interval will capture, the middle 95% interval, will capture the true value of the parameter 95% of the time. Of course, about 95% of the time. So if we repeat this process 100 times, about 95% of them will include the true value of the parameter. And maybe 5%, about 5 times will not. And from these 5 times, it happened the first time that we did today, which is this one. Okay, so it can happen that the interval doesn't include the true value, but based on the statistical theory of the bootstrap method, it will happen 95% of the time. It will include actually the true value of the parameter. So let's see a visualization for that. So this chart plots the assuming that we repeated this process 100 times, one line per time. It plots the interval, the 95% interval that we got. Okay, so the 95% interval from the first replication went that between this point and that point. The second one is between that point and that point, and so on. We stack all of the 100 times, 100 replications, 100 trials, all over each other. We got this plot. Now, what is the red line here? The red line here is the true value of the parameter. Okay, so for example, the first trial, the first interval included the true value. The second one included the true value, but this one, for example, didn't include the true value. This one didn't include the true value, and so on. If you looked at the figure carefully, you will see that about 95% of the cases, the interval included the true value of the parameter. So this interval is called 95% confidence interval. Okay, 95% confidence interval. And what that means is that if we repeat that process 100 times, 95% of the time the interval will include the true value of the parameter. So we are 95% confident that the interval includes the true value of the parameter. That's the meaning of the confidence interval, or 95% confidence interval. Of course, we can change this number. We can say 80% confidence interval, which means that this interval will be good 80% of the time. What do we mean by good? We mean that it will include the true value of the parameter. Okay, so that's what we mean by confidence interval. We are confident that this interval, 95% confident, for example, in this chart, these intervals, generally, of course, in reality, we don't do this 100 times. We are doing it just to show you what we mean by confidence interval. But in reality, we will do it just once, and we will say that this interval we have 95% confidence that this interval includes the true value of the parameter. Now, where is our estimation? So in our example, we were trying to say, to get or to estimate the value of the median salary of the employees in San Francisco in that year. So our estimation will not be one value. Our estimation will be an interval. So we will say that here is a 95% confidence interval. That salary goes from that value to that value with 95% confidence. And now you know how you can interpret this statement. That means that there is a 95% confidence that this interval will include the true value of the parameter. So 95% confidence interval is an interval of estimates of a parameter. So we will not give just one estimate, by the way. We will say that we have an interval of estimates and we have 95% confidence in that interval, or 80% confidence, or 60% confidence, whatever the interval that we compute. We know now how we can interpret saying that this is a confidence interval. So the confidence interval is an interval of estimates of a parameter. It's based on random sampling, as you saw in the Bootstrap method. 95% is called the confidence level. Okay, so if we have 80% confidence interval, so 80% is called the confidence level in this case is 80%. So that level could be any percent between 0 and 100. Of course, as it increases, the interval will be wider. If you decrease it, let's say 50% confidence, then the interval will be smaller. Okay, although the interval will be smaller, but your confidence will be smaller also. Okay, so 90% confidence interval, you have 90% confidence in that interval. Usually that will be wider than, of course, 60% or 50% intervals. So higher level means wider intervals. And the confidence, and this is very important point about confidence intervals. So the confidence is in the process that generated the interval. The confidence is in the process that generated the interval. The process generates a good interval about 95% of the time. What do you mean by good interval? It includes the value of the true value of the parameter. So that's a confidence in the interval, or the confidence in the process that generated the interval. Let's see another demo where we don't know the true value actually of the parameter. So let's get back to the code and work with another example. So the dataset here is a dataset that we used before, which is the dataset of new babies. Okay, we have one row for each baby with the weight of the birth weight and maternal age of the mother, the height, and whether they are smoking, the mother was smoking or not, and so on. So from this data, we will only in this demo, in this lecture, we will only focus on this column, which is maternal age. So what we want to do is to estimate the mean or the average maternal age of mothers. So here is the histogram of the maternal age. You see that the age goes from 15 to 45. Okay, we want now to estimate the average maternal age, the average age of mothers at when they give birth to babies. In this demo, of course, this data set comes from a hospital. Okay, it's not from the entire population. So we'll assume that this is the random sample that we have from the entire population. And that's why we don't know exactly what the true value is of the maternal age. But let's assume that this is a random sample from the population. Now the median, or the mean, the mean, not median here, the mean of the mothers in that sample is this value. So the median the mean is 27.2. Now let's do the bootstrap method. We will get, of course, this is the function that will compute, the function that will actually do the sampling, actually the resampling, because we assume that birth table here is the sample that we have. So we will resample and we will return the mean value. Now we want to repeat that 1000 times to compute the confidence interval, the 95% confidence interval. So we'll repeat that. We'll call this function 1000 times, and we'll compute the 25th percentile and 97th, the 2.5 percentile and the 97.5 percentile to compute the confidence interval. That will be 95% confidence interval. So we are running this. Here is the 95% confidence interval from that simulation. Okay, so the confidence interval that we got, the 95% confidence interval that we got, is 26.9 to 27.6. Okay, so to interpret that, we can say that we are 95% confident that this interval includes the true average age of mothers in the population, which we don't know. Okay, so it is between 26.9 and 27.6. Let's plot that. So this is the distribution of the bootstrap means of the maternal age, and this is the blue point is the median computed from the original sample. As I said, it is usually around the center of the distribution, and the gold line here is the 95% confidence interval. Where's the red point? We don't know it because we don't have the population in this case. Okay, so that's now the 95% confidence interval. Let's get back to the slides and talk about the meaning of the confidence interval, more about the meaning, and how we can use the method and also when we shouldn't use that method, the bootstrap method. First, can you use a confidence interval like the following application? Let's say that we have computed the 95% confidence interval for the average age of mothers. This is like what we just did in the population to be 26.9 and to 27.6. So this is the lower bound and this is the upper bound of the 95% confidence interval. So we computed that confidence interval. Now tell me or think with me whether the following statement is true or false. Here's the statement. About 95% of the mothers in the population were between 26.9 years and 27.6 years old. So notice that these are the bounds of the confidence interval. Okay, so this is the 95% confidence interval, and here's the statement that 95% of the mothers will have age within this interval. Is that true or false? Now, if you didn't take this course and you didn't watch the lecture, and I told you this statement, and I asked you to tell me whether this is true or false, what would you say? 95% of mothers, when they give birth, they are between 26.9 years old and 27.6 years old. Is that true or false? Of course, without studying data science and without watching this lecture, without knowing anything about confidence interval, that is clearly false. That is clearly false. So the statement about, or the meaning of the 95% confidence interval is not saying that 95% of the mothers will be within this interval. So this is false. We are actually estimating that their average age is in this interval. Okay, that's not about the distribution of the age. It's just an estimation. Okay, we are estimating that the average age will be in this interval. Okay, in reality, if you remember from the demo, this is the distribution of the age, and by no means that 95% of these values is within this small interval somewhere here. Okay, so that might be easy. Here is another one. Same statement, 95% confidence interval. Within this interval, with 95% confidence interval is this. And now the question is whether this statement is true or false. There is a 95% probability that the interval 26.9 to 27.6 contains the average age of mothers in the population. Okay, so given this 95% confidence interval, is this statement true or false? There is a 0.95 probability that this interval contains the average age of mothers. So what did we say about the meaning of the confidence interval? We said that when we say this is a 95% confidence interval, we have 95% confidence in this interval that it includes the true value. And if we repeat that process 100 times, about 95% of them will include the true value. So that's exactly the same like saying that there is a 95% probability that this interval contains the true value of the maternal age in the population. So this is true. This is yes. Okay, it is true. An interval generated from that process is good 95% of the time, which means that there is a probability 95% that this interval is good. A third one, same statement again about same confidence interval, but the statement that we want to check is different. So, true or false? There is a 95% probability that the average age of mothers in the population is in the range 26.9 to 27.6 years. So think about what we did when we compute the 95% confidence interval. Is it about the interval itself, or it's a chance of the true value of the parameter, which is the mean maternal age? Actually, it is a chance for the interval. So that's the actual meaning of the confidence interval. So this statement is false. The average age of the mothers in the population actually is unknown, yes, but it is a constant. It is not a random variable. Okay, so we are not computing a chance about the true value of the parameter. We are computing a chance, or we are talking about a chance of the interval. Okay, so the value, the actual value of the average age of the mothers is not random. It is just unknown, but it's a constant. It's a constant. It's not random. So when we say 95% confidence, it's about the interval, not the parameter. Okay, so we are confident that the interval contains the parameter. That's true, but it is false to say, or it is not statistically correct to say that there is a chance 95% that the parameter, the true value of the parameter, will be in that range. These are two different things. The first is true, the second is false. Okay, it might look a bit tricky. Think about it and you will see the difference. Okay, so we cannot say that there is a 95% probability that the true average age is in this interval. So that's false, that's incorrect. What is correct is the previous one, okay, the previous slide, when we said that there is a 95% probability that the interval contains the average age of mothers. These are two different things. Okay, so the probability is about the interval, not about the average age, because the average age actually is not a random variable. Okay, it's a constant, but we don't know it, and we want to estimate the value of it. Okay, now when not to use the bootstrap method. We should not use the bootstrap method if we are trying to estimate the minimum or maximum value in a population. So in the two previous demos, we computed the mean and the median. If you are trying to compute the minimum or maximum, or generally very high or very low percentiles, you should not use the bootstrap method. Or if you are computing any parameter, an estimate of any parameter that is greatly affected by rare elements of the population. Okay, and that's actually the general case. If you are trying to estimate a parameter that will affected by very few elements or very rare elements of the population, like the minimum or the maximum, then you should not use the bootstrap method. It will not give you good estimates. Also, you should not use it if the probability distribution of your statistic is not roughly bell-shaped. Okay, bell-shaped is like the normal distribution, if you are familiar with that. If we look at the distribution of the means here, it is bell-shaped. It's like the bell. Okay, so if your empirical distribution doesn't show something like a bell distribution, then the bootstrap method is not good. Will not give you a good estimate. Or, of course, if the original sample is very small. And we'll talk about that more, inshallah, in the next session. Now, is there any relationship between the confidence intervals and testing hypotheses? The answer is yes. In fact, we can use confidence intervals to do hypothesis testing. And here is how. Let's say that the null hypothesis is that the population mean is a specific value x. And the alternative hypothesis is that the population mean is not that value x. Okay, so for example, in our maternal age, let's say that the null hypothesis is that the population mean is 27. Okay, so the alternative will be the population mean is not 27. And let's say that the significance level or the p-value cutoff is p%. Okay, let's say 5%. P is 5 here. Here is how the confidence interval can be used for hypothesis testing. We will compute 100 minus p% confidence interval. So if p is 5, then we will compute or construct a 95% confidence interval for the population mean using the bootstrap method. Okay, so using the bootstrap method, we will compute 95% confidence interval. Okay, and how did we get 95? Is 100 minus p, which is the cutoff, the significance level or the p-value cutoff. Okay, so if p is 5, the significance level is 5, then we will compute 95% confidence interval. If p is 1%, then we will compute 99% confidence interval. After we compute the confidence interval, we'll check if x, which is the specific value that we are testing, is not in the interval, then we reject the null hypothesis. If x is in the interval, we cannot reject the null hypothesis, and we will conclude that the mean, we accepted the null hypothesis, and that we can conclude that the mean is that value with very high probability. Okay, so again, we use the confidence interval to do the hypothesis testing in this way. Okay, so that's the statistic that we will simulate, and this is the specific value, and we compare or we test whether this specific value will be within the confidence interval or not. And based on that, we check if the value is in that interval or not, and based on that, we decide whether to accept or reject the null hypothesis. In comparison to what we do in hypothesis testing, we just say that we accept or reject the hypothesis. But using confidence interval, we did actually one more step, which is that we give an estimate within an interval. Okay, so it's not only that we can say yes, it is that value with high probability, of course, or not, but we also give a confidence interval. We say that we are 95% confident that the value will be in that interval. Okay, or the value is not in that interval, and so on. There is a very nice example in the textbook. I want you to please read, and if you have any questions, you can ask me later. With that, we are done with the estimation session. inshallah in the next lecture we will start a new session. Assalamu alaikum wa rahmatullahi wa barakatuh.